Thank you for a very kind introduction. I'm here to present the seven deadly sins for applied machine learning and artificial intelligence in finance. But actually, these are sins issues that are shared by other industries as well. And my presentation will be two-folded. I will start by making connections between what you know about that are the classic seven deadly sins and what are seven deadly sins of applied machine learning. And then in the second part of my talk, I'll be talking about my company, my team, and how my team is mitigating some of the issues that I'm talking about on this talk. Okay, so I'll start with gluttony. Okay, and the concept of data gluttony. Okay, that we are living the era of data gluttony that we are living nowadays. So many executives and board members around the globe have this idea that okay, we have a lot of digital data, and the value proposition of cloud systems plus machine learning libraries, methods, functions. Here in my slide, personalized by Bob, is that you can fit all the data you have into Bob and expect Bob to change the world. And change the world for you, it's to get, for instance, a 30% uplift of your business output. And of course, this is a completely unrealistic expectation. This is something that really would not happen. There are many reasons for this being unrealistic. I'm picking one specific reason to that, which is time, or the concept of time passing by, or the concept of time dependency that many businesses have. Okay, so if we think about e-commerce, for instance, and we think about so nowadays we are living in a global crisis with the so-called coronavirus, and you have products that typically will not have a shortage of supply that now have, such as toilet paper. Okay, that's something that completely unexpected. But there are also other issues related with the time, not only special events, but actually issues depending the time of the day or actually the day of the week you are or the season of the year you are. That these dynamics of time they don't cope well with some of the assumptions, the mathematical assumptions that are behind some of the mainstream machine learning methods that are out there that you guys use on a daily basis. Okay, I pick here two, which is independent and identically variables, or such so-called IID assumptions and stationary distributions. Okay, which don't cope very well with dynamics of time. So, in terms of, for instance, you look to YID. IID it's basis to a certain series of theorems that are on the backbone of many of these algorithms. And if you look, one of the things that IID assumes is independent variables, right? So when you look, for instance, for banking systems, two of the most important variables to describe a customer are their income and their credit bureau rating. Okay, so, and obviously, people with very high income are much more likely to have a very good credit bureau rating. So these two concepts are different, but they have some dependencies among themselves. And you can extend these examples to many other application cases on many other industries, okay, that they will have. This gets amplified wherever this as a time bias, okay? So such as, for instance, you got like a raise on your income or temporary a certain bonus, okay? So this is an unexpected effect that somehow that you would not pick up, but your algorithm, machine learning algorithm would. Okay, same thing for stationary distributions. So stationary distributions, what they say is the concept that you try to learn, okay, it does not vary over time, such as the stock price. Okay, the dependence of the stock price of company A tomorrow, based on all the history of stock price of this company. Of course, what happens is there are always factors that are exogenous to the data that you have that affect your target. Okay, and so they affect your target. The relationship between these variables that you have and your target, talking about supervised learning, will change over time. Okay, because that's the way you model it. As many algorithms simply don't assume that this doesn't happen. Okay, and that's a big problem. And the more data you feed into them, the more you suffer from these biases. And you will see that in other examples during this presentation. Okay, so the second thing I want to talk with you about is about the rot, our rot with the law, our desire to not follow the law, to not respect the law, to not comply with the law. And let's do this in the context of startups. Okay, when you have a startup, a business idea which is driven based on machine learning, so you go out there, you get some seed fund, you start it, you have some POC, you have some customers, you have some promised business numbers. Series A or Series B investors love you. Then you start making some buzz in the market, and then regulators come. Regulators come and they ask for details. They ask how you are doing things, how you are securing the privacy of your customers, how your models are making decisions. Are they being biased? Are they being fair? Are they discriminating? And how they are discriminating? And of course, perhaps when you just started your company, you are thinking about, making business. Huh? So adding value. You are not looking into a more regulatory aspect of it. What will be the implications in 12 months, in 18 months, where will be on a Series B stage of having such system worked on such a big scale. And of course, if you have a simple model, they will be easier to interpret, but they don't provide such a business advantage. Complex models work, but typically they are not interpretable at all. And when you reach this stage, it's too late. So you cannot turn to regulators and say, hey, you know what? Typically I use this model, we produce the results, but now we are changing, okay, to other type of models. This will not help you to build trust. And this actually, for regulators that are not tech people, will even sound somehow fraudulent. So you'll have problems. You probably will not be able to execute your business plan in the time that you forecasted to. You may even risk to get fined or shut down. And there are unfortunately some examples of some companies that went over that, particularly after GDPR legislation comes into place. Third thing I want to talk with you is pride. Okay, the pride to be big. So we live in a society in general where big means good, big means great, big means better. Okay, because we are taught so. We have all this predefined idea of already from our education and from our background. This is true, and a good example of that. US is even bigger than in the rest of the world, I would say. And there is this company that's called Digital Reasoning that in 2016 made huge headlines on. So basically, that trained artificial neural network that had 160 billion of synapses, which correspond to 0.16% of human brain, and that was the Guinness record for size of a neural network. Okay, by then they made like huge buzz. But let me ask you one question: have you ever heard from digital reason of digital reason since then? No. And the answer, the reason for that is that size doesn't matter. Okay, accuracy does. Okay, but size doesn't. So, and in order to explain you better this concept, okay, that we're trying to show you here, that the performance of your model is actually the accuracy that you get versus the resources you need to achieve that accuracy. I have here, in terms of business, the business value of the model I try to achieve. I went to the internet and I brought from a very known tech blog this post where there is this data scientist that created a convolutional neural network that works great. It was training for 10 hours with a very complex set of CPUs and GPUs, and they achieved an accuracy of 99.999% of accuracy on testing examples, but then he couldn't deploy the model in production because the prediction time for testing examples were just too slow for his business application. Okay, so the business, although this model has an accuracy of 99.999% over test cases, the business value of this presentation is actually of this model is actually zero. Okay, so this is something that you guys have to be very careful about when creating models. Okay, accuracy, size doesn't matter. Accuracy is important, but resources are also important. Okay, so fourth thing I want to talk to you about today is slot. Slot in the sense of automation. Okay, so many businesses seek automation as the ultimate holy grail. So the idea is interesting. So you have an automated business, so that means that your bank account is increasing always without you doing basically nothing to do that. But what actually many people think that automation means, it actually means digitalization. So many businesses nowadays, even if they operate in digital, they rely either on end users manual entry or manual data entry made by low income employees. Okay, and guess what? These stakeholders, these people, like for instance, customers, are lazy. Imagine that you think about yourself. When you want to buy a product on the new e-commerce website, you have to fill a form with a few information like the one you are seeing here on the left side of the presentation. And if you think about yourself, you don't care much of setting the most reliable set of information. You just get done with it. Okay, so they just want to buy the product and get the possible user experience with the minimum possible effort, and this leads to mistakes and a lot of mistakes. And in machine learning, people will say that these mistakes on data entry will lead to noise, and some machine learning methods actually they cope well with noise. But I would like to contradict this, okay? Because this noise in machine learning, noise typically assumes that the errors happen at random. And these errors of data entry, they typically don't happen at random. They happen due to an inefficient design of the interface, for instance, when you look to forms. I give you an example of this. Imagine that you have to set your profession and you have a combo box with 30 entries. Okay. Typically, if you have 30 entries for a profession, there will be overlap between 2 or 3 different entries. So 2 or 3 different entries will be a fairly good approximation to what you actually do. But what typically happens, you pick the first that you see, because it's better than to scroll down and see all the options and think of what you really need to enter. And so you'll have always a bias, you see, to the first 5 or the first 10 elements of the combo box. And these will not generate noise, will generate an error. And an error is a pattern that your machine learning model will pick. And an error is a pattern that your machine learning model will make your machine learning model to underperform. Okay, these type of data quality issues are usually the first cause for low performance of a machine learning model in production, and they are underlooked. Okay, they are underlooked because it's not sexy to say that. Okay, we fixed 2 or 3 bugs on our back end, so now our machine learning models are performing better. It's better to say, no, we retrained the new model, deep learning, super hyper model with a lot of layers that is doing better than the previous one. Okay? So, and also it's very hard to track the origin of these mistakes. So it's very hard to actually isolate and say, hey, you know why? You know what? The problem of our model performance is actually the front end team that is not designing the form well. Okay, this is something in the company, especially it's already mid-sized. It's it's a story very hard to stick, but probably it's also true. Okay, so that's this slot of the customers can be really a problem and a reason for failure of your machine learning models. And of course, talking about customers, we have to talk about greed. Okay, So customers typically care about themselves and not about your business. So if they can get the maximum amount of product with the minimum amount of money, they will do it. Okay, and in banking world, this means low banking fees, low mortgage interest, get a larger payday loan. They want to get it, and they will do everything they can to get it. And of course, they are unreliable. Okay, so if to get a loan, they will need to overstate a bit for their income. They will do that. Again, think about yourselves. And an example like filling a tax declaration. Okay, I'm sure that there was some at some point you found like an invoice to say, okay, this invoice is not really the type of thing that I should put on this section, but I'll try it out. Okay, and well, let's say this way. This is a type of fraud. Okay, that's this small increase on the stated income. This is a small invoice that we shouldn't put on the deductions of your tax declaration, and you decide to put. And of course, there is a big difference between these and real fraud, like impersonification, forged documents, credit card cloning, and so on. But from a data perspective, this goes exactly on the same direction and will cause you exactly the same type of problems. Okay, so from a data perspective, it's pretty much the same. And if you think that your operations, normal operations, human-driven operations of your business, would suffer from this type of mini frauds, let's say this way, this type of unreliability of the data that customer provides, if you have machine learning models in production, you'll suffer more. Okay, much more. Okay, because these will be amplified. The machine learning models will pick on these try to pick on these erroneous fraudulent patterns. That's not good. Sixth, but not the last, I would like to talk about what I call lust or vanity of data scientists. So as we know, there is a huge hype on data scientists nowadays of being a data scientist. Everyone wants to be a data scientist. Everyone thinks that they can be a data scientist. And then, of course, there is some our status that to be a data scientist is somewhat better. So I'm not a programmer. I'm a data scientist. I do analysis. I don't do code. I do models. I don't do heuristics. So somehow they judge themselves a bit better than the common software developer, let's say this way. But from a business stakeholder point of view, they are still treated the same. So if you think about, for instance, a technical recruitment agency, nowadays they are still very focused on technologies. Okay, so that's fair because different teams also in many organizations are organized by technologies. So you have your back-end team running in Scala. You have your business intelligence team that runs basically manages MySQL databases, let's say this way. Then you have your data warehouse team that manages NoSQL databases. Then you have also the data science team that manages programs in R or in Python. Okay, but the message that I want to bring you here is the most important tool for data science is the brain. Okay, and the ability to connect the dots between business requirements, data that you have available, and the tools that are out there to solve the problem. Okay, and these true data science with this ability are extremely hard to find, and those are the ones that are actually can boost your business to the next level, the so-called unicorns. Okay, the others are what I call citizen data scientists, but they are not much better, let's say this way, or much. They are not more important than software developer in other teams. They have their function, but they don't bring you necessarily to the next level standalone. So, but because there is this lust, this vanity, this hype nowadays, people tend to overvalue them and overvalue also from a salary point of view, of course. So be aware of this when building, when hiring, grooming, and making plans to retain data science talent. And finally, the last scene is envy, and envy for the neighbor with machine learning. So again, following the hype, many companies have on their business plans to have machine learning, to have AI. Actually, nowadays you see that many companies even have AI in the name, .ai. You see, when I see a company with .ai, I always oscillate because I think if you need to have .ai in the name, well, are you really doing AI? So what happens with this hype is a bit like the teenage sex type of hype, right? So everybody thinks that others are doing it. Everybody wonders they can do it too, but nobody or very few are actually doing it. Okay, so this is true for startups that do what I call the PowerPoint AI. Okay, they have a lot of ideas of AI in PowerPoint, but then in actually they are doing just the analytical dashboards or some models to forecast the financial results, but nothing core to the business. But it goes also to measure companies, such as, for instance, in automotive industry, you hear talk a lot about AI and applications to AI, but you go to see their business, the most profit comes from making cars, which doesn't actually have a machine learning model running there, right? So they may have some recognition of pedestrians, they may have some control system that resorts to some heuristics, but it's not their core business. Okay, it's not the core feature from the car, which must core feature is that you drive and that you can drive safely. And typically, this nowadays for many companies, it still is not there. Okay, and perhaps it doesn't need to be there, and that's the message a bit that I want to make with this slide. That perhaps not everybody should be doing it. Okay, in order to use machine learning in their core business, you need to have the right data, the right scientists, the right infrastructure, the right business questions to ask, and to understand which are the implications down the line of making that decision. For instance, I already showed an example what happens of the law implications of doing that, the regulatory implications of doing that. And in reality, we have a lot of organizations like this Rome Transit Agency was a previous customer on a previous organization I worked for, which makes statements like this. We have tons of data, digital data, but we are not able to use machine learning, neither to hire experts to do it. So, okay. So if you are using machine learning, and in the sense of this Gartner chart, you are using that on your core business to do predictive analytics, a prescriptive analytics, you have to be aware of the bias loop that we are going into. So if your data have already a bias, and now let's talk about bias in more common sense, like a gender bias. Let's say that we have a data set of images that we're trying to predict the activity of that we are seeing on the image, and then we have also a series of more classical features to have it so, and one of the features is the gender of the person. And in this data set, for within all the persons that are actually cooking, 67% are women. Then we have a test set out of it, and we went to make predictions of what this algorithm is able to do on the test set, and we see that 84% of the time that the algorithm predicts cooking as an activity for the image, you have actually women in that image. Okay, so and this is there was a bias on the data set that was not only mimicked by the machine learning algorithm, but it was amplified. Okay, and if you have this model in production, so this machine learning algorithm will be making decisions that affect your business, yes, but that affects also your data collection and your collection of labels. So what will enter is in a bias loop. So later on, you retrain your model, and your data set will not have 67% of the people cooking as a woman, but you'll have 84 or 80. Okay, and then you retrain a machine learning model on that and put again in production. So when you enter in this bias loop, and this bias loop, of course, what means is the machine learning model is underperforming, which means that your business is underperforming instead of overperforming. So you have to be very careful for what you wish for, because you may get it and may not be what you are hoping to get. Okay. So after I went throughout all these seven scenes, I will talk a little bit about Monedo, my team, and the solutions we are looking to some of these challenges. Okay, so Monedo, that by the way was Kreditech till last week, where we decided to go for a rebranding. The company that is already out there for 7 years, and we operate on the consumer lending business. Okay, so giving loans to people, small loans for private for their private usage, and we were able to borrow more than 600 million euros in a completely human-free fashion. So there is no review of applications by humans. There is no postponing. Application is either gets accepted or rejected based on offer personalization engine, which is fully enabled with machine learning. Okay, so with different machine learning services and components, and this is the team that is enabling this for happen as of now. Okay, and we, in terms of R&D, we focus on a lot of topics, a lot of buzzwords, AutoML, interpretability, reject inference, fraud prevention, outlier detection, and so on. And by the way, we are hiring, so if you guys are interested on looking to this, please drop me a line on Q&A or even after. And I will be talking about on this presentation a little bit about some of these problems and how we are working towards mitigating them. And by the way, by mitigating them, mitigating some of the scenes that we saw earlier on the first part of this presentation. Okay, and starting with data gluttony. Okay, the best friend of data gluttony is feature selection. Okay, so where we drop data points, and this one of the ways of doing that on an unsupervised fashion is correlation. Okay, and different types of machine learning models, they are more sensitive to have or not have correlated features as input. In the case, for instance, of tree-based models, typically you don't need that much to remove highly correlated features in order for them to perform well. But if you do, you may decrease your training time and the complexity of your model, so you may decrease the resources that you need. And as you saw before, that's a good idea, right? Because that increases the performance of your model overall. Make the model easier to deploy, easier to maintain, easier to track, with less features, so easier to monitor as well, and that's a good idea. And if you go to do that for tree-based models, you go with Spearman, okay? Because tree-based models typically use entropy type of criteria, so they look to features and they try to find splitting points, which after the feature being ordered, let's say income, okay, they try to find something like, okay, for incomes above 5,000 euros a month, all the customers repay the loans in time. Okay, and then for customers between 5,000 to 2.5, so just 0.8 or 0.7 and so on. So, and Spearman actually is the best approximation there is. It's very close to linear correlation, which is Pearson correlation, but it's the most natural choice for what there is of correlation coefficients out there to do these unsupervised feature selection. So I've brought here a synthetically generated example to try to illustrate why this is not a perfect solution. Okay, so Spearman correlation coefficient, also similar to other correlation coefficient, is symmetric. So correlation of A to B is the same of B to A. And in the case of the features that we have on the example, this is 0.98 or greater. Okay, so this is actually, it's very, 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 very high. And you would tell me, okay, this is okay to remove one of these features and use the other for modeling. Okay, so when you look to the features, they actually looked also very similar as well. So we have one red feature, which by the way is normally distributed, and the blue feature is also normally distributed, also with the same mean, with the variance slightly different, but it's somehow ordinal, right? Because you have those steps there that change only in the series of values, but they are very close. This is why you obtain this Spearman correlation coefficient. And then you have a third variable, which is a target binary variable. You can imagine this to be, for instance, a probability of default that, actually not a probability of default. I'm sorry. So a concept like type of concept like good bad customer, where good is a customer that doesn't default on the payment, and bad is a customer that defaults. And what you want is then to build a model that gives you the probability of default for each customer, right? So, and this, imagine that you have such target value, and it follows very well both the red and the blue features. So they are very good predictive, have a very good predictive power. Very, very, very good. So what we want to do is separated the data set into training and test, this synthetic data set, and we run directly for each one of the features. So for the blue feature versus the target, and for the red feature versus the target, we run the area under the ROC curve, okay, for these features. And you see that, they tend to agree with the Spearman correlation coefficient, saying that, the predictive power of both is more or less the same thing. Okay, so one is unsupervised, another is supervised because it looks to the target. They say they're the same thing. But then we run a different type of experiment. So we'll train a random forest model with another trees over the training. One model using only the blue feature and another model using only the red feature. And then we run again the AUC, the resulting AUC over the test. And that depicts a different picture. So you see AUCs are very high, but for the red feature, the continuous one, it's 0.96, and for the model with the blue feature is 0.94. And then you ask me, hey, Louis, but perhaps that was just pure luck, because there is a lot of randomized. You generate your features once, you train your models once as well. But okay, I did it 100 runs, and here you have the density of the AUC of the resulting models for each one of the runs. And you can clearly see that the mean is different. Okay, if you run any statistical test over this, will tell you that the mean of the two distributions is different, and you can visually see that the red feature is actually produces if you train a model with red feature, this model will be slightly better. So the problem is the correlation coefficients are symmetric, where entropy-based measures actually favor dense and continuous features like the red one, with a potential infinite number of splits. So in order to not follow the fallacy given by the correlation ranks, but to be able to still to have low dimensional models and be able to be resource aware, we in the team created this asymmetric Rayleigh coefficient, which is something that uses tree-based processes very fast in order to say if we can replace one feature with the other, and exploring the rationality. So not only that we can remove one of the features, but which one of the features we remove, and this without looking to the labels, never looking to the labels. So, and these the results we see is that, okay, if you try to remove red and keep the blue one, we shouldn't do that. But if we try to do the other way around, remove the blue and keep the red, we can do that. Okay, so that's the type of result we are looking for. Okay, and still keeping trying to avoid data gluttony on the sense that we described before. The second problem we try to mitigate is the greed from customers. And of course, in a banking system, that will be on one possibility is on the affordability estimation. So affordability for us concerns which is the maximum monthly installment size that I can grant a loan to the customer that will guarantee that you'll repay me. Okay. So we try to model this as a survival analysis problem, okay, where we have a series of features such as bank transactions, judicial orders, also things related with open bills that the customer didn't pay, and other type of features. And we try to get a curve that tells me, okay, for if I grant him a loan with an installment size of 50 euros, you have a probability default of zero point 0.8. If it is 55, it's a 0.75. If it is 100 euros, it's zero point 0.5, and so on. Okay, we used random survival forests to do that. Okay, which is a fully non-parametric way of learning survival curves. And we had 3 tricks to make this model work. First is that our problem is not really a right-censored survival problem in the sense as follows. So if we have a customer that we granted, for instance, 100 euros and they repaid fully his loan, we can be sure that if we have granted 80 euros, he would repay it as well. But we don't know if we granted 150, if he will repay or not. So this will be a censored point. But if we have a customer where we granted a loan of an installment size of 80 euros and he defaulted, nothing guarantees us that if he would get a smaller loan, let's say 50 or 60 or 40, he would default or not. So this is an assumption that traditional survival analysis does. So what we do is to artificially introduce some noise in our labels in order to handle this problem and keep the assumptions, the mathematical assumptions that are necessary to model the problem as a survival one. The second trick we have is, okay, as we do this thing with the labels, we cannot use the traditional evaluation metrics that are used in survival analysis. So we derived our own business-centered tuning and evaluation framework, which allow us to set with the best probability threshold to operate, okay, and what type of effects in profits we expect. And here we see that, okay, we selected this threshold based on some criteria, and we see that the expected uplift to a scenario that we have previously in production is actually something around 25%, which is good. And everybody celebrated in our company the achievement. Great model, 25% uplift is great. But then we went to see the size of the model in memory, and that was 150 gigabytes, okay, with a response time of 100.2 seconds. So there is no Superman. We cannot put this in production. Okay, we are super proud of our achievements here, but here we were completely depressed. So the third trick we needed to do is we need to devise a loss function that comprises a trade-off between accuracy and the resources that the model needs to use. And with that, we tried to tune the hyperparameters of our model learning process in a way that find a model that can be deployed but perform well in terms of business. Okay, this slide has a lot of details about what parameters this was, but this was the main idea. Okay, and this worked very well for us and allowed us to achieve not the 25% that I've promised you earlier, a bit less, but still something that can actually be deployed in real world and can actually work. Okay, so I know that just to finish the presentation with a touch of reject inference, which is a problem that also affects a lot financial systems. So it's a problem. Let's say that we have a credit scoring, and we are deciding which customers to accept and to reject. Typically, we accept a very small percentage of the customers. Let's say 20%. And these are the customers we will issue a loan for, and which will have material to construct labels in the future. So when we go to train a new model, this model will be based only on these 20% of the accepted examples, and will be biased. okay, bias, because these examples will have distribution, so the incomes of these customers will be higher than most of the incomes of most of the customers that this model will be seeing in production. So the gap of performance, the performance loss due to bias, will be very high to be neglected. Okay, so we need to do something about it, and that something in Monedo is the shallow self-learning framework. So this operates in three steps. First, initialization step we call filtering. What we do, we train an outlier detection method for high-dimensional data, such as an isolation forest, that aims to understand. So we train it over accepted data, and then over the rejects. Basically, what we will do, we'll try to remove cases that for which we don't have a label that are very different from our accepted cases. And then we have strong learners, such as a neural network or a XGB classifier, that learns a model from the accepted cases. But then we have another machine learning model, in this case, a linear model, that also tries to make the same thing. And this model will be weaker. So the main idea, but its output, its probability of its output will be more calibrated. So we'll take less risk. So when this model says there is a 98% chance of defaulting or not non-defaulting, this model will take less risk. It will be more times correct. So we use this model to label rejects under certain, considering the risk of label them incorrect. Okay, and we have then an iterative loop. Okay, that we label, we append to the training set, we retrain a strong classifier, and we retrain a new label, and we go again, and we go again, and go again, until certain stopping criteria is met. Okay, so we evaluated these on a data set, both with accepts and rejects, and an unbiased sample, so a series of applications which were accepted as random, okay, without bias. Using this unbiased data set, we compared to many other reject inference techniques from the field, and we can see that we have somehow a raise in performance. Also, we went to explore popular methods in the machine learning community, reweighting methods, and again, so methods that try to give more weight to certain examples that we know that are more likely to be on the population distribution, but on the accept distribution will be reduced. And what happens is our method also outperforms these ones, and the result of this research, this R&D, was presented on ECML PKD 2019, which is the most relevant conference on machine learning in Europe. So also in terms of business, although the difference on the numbers seems small, you can see that the potential gains for business are big. And we measure that. So these small numbers can mean $100 million, which is a lot of money, okay, for our business. So this really ends my talk. They have here some final remarks that I will give to you as a take-home lesson. So size and scale do not matter, performance does. Careful with what wish for, especially the machine learning. You may end up having it and not being your dream. Data scientists are unicorns, yes, but good business is also an unicorn, okay? And this is what you are a data scientist to have good business, and not just because for the sake of having data scientists. So customers do the unexpected, so they should expect that. You should never rely on data quality on the customers, so you have to have strict protocols to control this. Of course, when you think about machine learning, the tools are as good as their users, okay? So machine learning is not an exception. So it's not a one-fits-all type of solution for your business. Finally, sample bias is a big problem, especially for more mature organizations where they already have machine learning in progress, in production, controlling not only the business, but the way you collect data. And reject inference is a solution that can help you out.